right, now I'm going to try to give you some samples, examples of these different statistical tests. So I'll give you this Excel worksheet because it'll help you, I hope. So let's look at our first example. First of all, here are some of the, just as a reminder, the different mu and sigma. Sometimes it's difficult to remember what all these different things mean. So here are all our definitions for you. Let's jump right into an example. A future Ivy League high school, the average SAT score of 120 students on math is 570. The national average score is 550. The population standard deviation is unknown, so we calculated the standard deviation of the 120 students and found it to be 80. Now, intuition's kind of hard to say whether there's a statistical difference. Obviously, the scores at future Ivy League high school are higher than the 550 national average, but not sure if it's enough. So let's go step by step. First of all, the goal is determine if the SAT scores are higher for future Ivy League high school. We're not interested in them being lower, so right off the bat we've got kind of a one-sided tail. We're only interested in the upper right part. So our null hypothesis would be, remember the null hypothesis is assuming the status quo. The null hypothesis would be less than or equal to the current average SAT scores of 550. And what we're trying to prove in is that Ivy League, future Ivy League high schools, superior students, and so their SAT scores are higher, greater than 550. Second step, if we're using the critical values, is to assume an alpha. Remember, 0.05 would be a 95% confidence interval because it's 1 minus the alpha. If we wanted to make the constraints tighter, we could put 0.01 in there. In this Excel spreadsheet, you can use to put in whatever numbers you want. Step 3 is to let's put in some of our data and calculate the test statistic. Remember, the test statistic is going to tell us how far away from the mean our sample is on a standardized basis. And it's going to do that by calculating the absolute value, absolute distance away from the mean we are, divided by the standard error to give us a standardized distance. It basically is going to say we're X number of standard deviations away from the mean. So if our test statistic is bigger than 3, we know we're quite a distance away from the mean. If it's 1 or 2, we know we're not so far. Anyways, our hypothesized mu is 550. Sigma we do not know, so we'll substitute and use the sample. That tells us that we're using a test statistic of a t-distribution because we don't know what sigma is. So our sample size is n. Oh, by the way, anytime we use the test statistic, remember we're going to have to subtract 1 degree of freedom because we're basically assuming an S because we don't know what sigma is. Our sample size was 120. Our sample mean was 5.7. Now, put this out here. Sometimes you know people aren't going to be as kind as give that to you. In real life, you'd probably just have a sample data, so you'd have to do that range and calculate the average yourself. But we gave that to you. Here's the alpha again. Here's a couple options. A type of test. Well, we're interested in the one side tail to the right. We're not interested in the tail to the left. We're not interested in a two-tail. We're not interested in learning if the students are at Ivy League high school or not as smart or below the average SAT. We're only interested, it only proves our case if they're superior to the average. So we only want, it's got to fall way to the right, way superior to the 550. Here's our sample error, and here's the equation. Remember, it's our standard deviation divided by the square root of our population. And that makes sense, right? The standard deviation is going to shrink, get smaller as we get more and more samples. We're going to have less dispersion or less deviation, or another way is more consistency the higher our sample size. So that's going to shrink that standard error if we have a very high n. And it's also going to be, if our standard deviation is small to begin with, then that's going to help us shrink that standard error. So our test statistic is then simply taking our x bar minus our mu minus our average divided by the standard error. So our S bar was 570, so it was 20 away from the hypothesized mean divided by the standard error. That gets us a test statistic of 2.7 round numbers. So that means we're 2.7 to the right of the standard deviation. Or to the right of the mean. 2.7 standard deviations to the right of the mean. That's pretty significant to the right of the mean. But is it far enough? So that's the next question. We can either, steps 4, we could do conjoint. One way to do it is to calculate the p-value. Now remember, the p-value is the probability that I would get these results 570 or greater just by chance. Well, the probability of doing that is we can go to Excel and use what's called the t-dist. We're using a t-distribution, and in the t-dist what you do is you put in the first thing it asks you is, what is your test statistic? Well, how many standard deviations were you to the right? And if you remember a t-distribution, it changes, the distribution changes with the number of degrees of freedom. So here's our degree of freedom, which is our sample size minus 1. And that tells us that the probability of getting this is 3.5%. Now there's another tool within Excel that notice up here I had to do 1 minus the t-distribution because remember Excel goes from left to right, so it would have given me, if I didn't put that minus 1, it would have given me the probability from negative infinity up to a score of 570. So that's why I did 1 minus 1. If you don't want to do that, Excel has a new tool called tdist.rt for a right tail. And if you use that function, you just don't have to do the 1 minus 1. And notice you get the same thing, 0.356% that this would happen by chance. So the probability that this happens by chance is pretty darn low. So that would cause us to reject the null hypothesis. The null hypothesis is that Ivy League is 550. We would reject that and say, no, the kids at Ivy League High School are significantly better on the SAT scores. Now we could also do it another way. We could do it is to figure out what the critical value is. So for that we'd use the TINV. This is basically the hurdle point. And this says the hurdle point, it has to be 1.65 standard deviations to the right of the mean. And we're 2.7, so we're much farther to the right of that. And that makes sense because remember this 1.65 is the probability that there's a 5% chance because we got a 95% confidence interval or a 5% alpha. So same thing, we would reject. The null hypothesis would be the conclusion, i.e. the future Ivy League SAT scores are higher than average. There's only a 0.3% chance it happens by chance. Our test statistic is way outside of the critical value. So hopefully that's one t-distribution. Another t-distribution would be, another example would be using a two-tail. Let's assume a factory wants to know if the weight of a item is not up to specification. If the weight is 30 pounds, yesterday a sample of 300 had an average of 29.7 and a sample standard deviation of 3. So again, because we don't know the population standard deviation, we'll use the sample standard deviation as a substitute. Now this null hypothesis is a little different. We're not interested in, are they significantly more than 30 or significantly less? Either one is not good, right? We don't want the weight to be too high, the weight to be too low. So now our null hypothesis is that it equals 30, and we reject it if it's less than 30 or greater than 0, so 30. So we have a two-tailed test. Input the same stuff, same sort of thing to calculate the test stat. Here you can use use two tail if you want. If you don't use one tail, you have to multiply it by 2. Multiply this result. So you might want to use the t-dis 2 tails. Same thing here. And what we see is we do not reject the null hypothesis because there's an 84.4% chance that we would get these results by chance. And we notice that our test statistic is not inside the value of the critical ranges. The last example is a proportion. And let's say John is assumed to be a 70% foul shooter. You watch him one day, he makes 18 out of 20, 90%. Is John better than a 70% foul shooter? Well, again, we want to determine if John shoots better than 70%. It's a one-sided test, right? Because we're only interested if he shoots better. Alpha in this case, let's say, is 0.05. So our hypothesized proportion, pi, is 70. Our p-hat, our observed proportion, is 0.9. Our sample size, our alpha, we're only interested in a one-sided test. Again, we calculate our standard error. It's a little different here. It's kind of interesting. If you think of somebody as a 90% foul shooter, that's very consistent, right? They consistently make it. There's very little deviation, as opposed to a 50% foul shooter, where there's lots of deviation. So the way you calculate the standard error on a proportion, I find kind of interesting. You take 1 minus the proportion times the proportion divided by n. Obviously, as the sample size goes up, our consistency will get better, or another way of saying it, our dispersion will shrink, or our standard error will shrink, right? And then the test statistic is just our observed variance. How far away was p-hat from pi divided by what our standard error is. And then we go to Excel and do the same things, except use a because we now have a different distribution. We use the norm.sdist and the norm.sinv. And in this case, we reject the null hypothesis. There's only a 2.5% probability that he would shoot 90% by chance. And we're at a 95% confidence interval. Now note, if it was a 99% confidence interval, we wouldn't reject it because to accept at a 99% confidence interval, the p-value would have to be 1% or less. It's interesting. Hopefully you're seeing that as the test statistic gets very, very large, the p-value is going to get very low, right? Because the test statistic is going to say how many standard deviations are you from the mean. So if you're 3 or 4 or 5 standard deviations from the mean, your p-value has to be very, very small because there's a very small probability of that happening. There are 3 examples. The normal distribution would be the same, except you'd use normDisk Excel function, and of course you would know the population standard deviation, the sigma, so that you would go ahead and use that as opposed to using the sample standard deviation. Hope these 3 examples help. I'll give you the Excel worksheets and you can walk through them on your own. Thank you. Have a good day.